Well, students, we are discussing the fixed point iteration method. In this, we have seen all the conditions that we have to impose on the iterative function in order to make the fixed point iteration sequence a convergence sequence and the limit to be a fixed point of the iteration function. And thereby, we are now ready to state our convergence theorem on fixed point iteration method. Assume that G is continuously differentiable on an interval AB and G is a self map. Further, assume that G is also a contraction map. Recall that if modulus of G dash of X is less than 1 for all X in the interval AB, then we say that the function G is a contraction map in the interval AB, right? So this condition therefore says that G is a contraction map. These are the hypotheses of the convergence theorem. Now let us see the conclusions. The first one is that the function G has a unique fixed point in the interval AB. So we denote the interval AB by I, and G having a unique fixed point is equivalent to saying that this equation x equal to G of X has a unique solution R in the interval AB. Because if you put R is equal to G of R, it means R is precisely the fixed point of the function G, right? Strictly speaking, this conclusion is not a result in numerical analysis. You would have seen this result as an easy exercise in your real analysis course itself. Therefore, I will not get into the proof of this statement. Rather, I will give you an intuitive idea of how to prove this. Then you can complete it by yourself. As we have assumed, G is a self map in the interval AB, it means it takes values also in the interval AB, right? So let us consider this square A to B, assume that it is a square. And this is the line y is equal to x, G of A here, and it takes the value G of B somewhere here. It means this is your A comma G of A, and say this is the point B comma G of B. Again, recall why we are restricting our values of G in this interval, because of the assumption that G is a self map. If that is so, and also given that G is continuous, its graph will be something like this. It will not surely have any jump in it. Therefore, surely at some point, it has to cross the line y equal to x, right? That is how we say that if you have G to be a self map and if it is a continuous function, then G will surely have a fixed point. Note that these two alone will not give you guarantee for uniqueness, because this graph may cut the line at 2 points also. Say for instance, the graph may be going like this, right? In which case you may have more than one fixed point of the function G, right? One is at this point, and this point. So you have 3 points here in this case. So just continuity and self map cannot guarantee uniqueness. Now, who guarantees the uniqueness here is the contraction map. Why it is so? You can see that if the graph of the function G had crossed once this line, and now if it has to cross once again, how fast it has to grow, you see, it has to grow more than the growth of this line, right? The growth of this line is 1. That is, the slope of this line is 1. Therefore, G has to grow more than 1. It means G dash should be greater than 1 at some interval. Then only it can go beat the speed of this line so that it can cross it. So in this interval, your G dash must be growing more than 1 in order to again meet this line. That violates your assumption that G is a contraction map. Therefore, if G is a contraction map, then once it crosses the line, then it cannot grow more than 1, and therefore it has to stay below this line and touch f of b somewhere like this, right? Therefore, it has to be unique. So I'm just giving you a geometrical picture which you can now rigorously write in mathematical statement and prove it. Anyway, you would have done it as an easy exercise in the real analysis course. Let us go to the next conclusion, which is more relevant to numerical analysis. It says that for any choice of x0 in the interval AB, if you generate the sequence in this way, that is xn plus 1 equal to g of xn, precisely the fixed point iteration method, then the sequence will converge precisely to the unique fixed point R. That is what the statement says, which is also what we precisely want to prove. And not only that, it gives you a nice estimate also for your mathematical error xn minus R. If you recall, we got such a estimate in the bisection method, from where you can also obtain the number of iterations needed to achieve certain tolerance to the mathematical error, right? In fact, this can further be written like this, and this can now be used to find n in order to have some tolerance. Say, for instance, if you ask me how much iteration should I perform in order to have the error less than, say, 10 to the power of minus 2, then what you do is you impose this condition less than 10 to the power of minus 2 and take logarithm on both sides, and from there you can compute n. See, this luxury, if you recall, we had in the bisection method. We did not even have it in the regular falsy method because the interval may not shrink to a point, right? That was the problem in regular falsy method, whereas in bisection method, in the limiting case, your interval in which you are locating a root will shrink to a single point. Because of that property in the bisection method, we got an estimate from where we could compute the number of iterations needed without the knowledge of R, as well as without going for an explicit calculation of the iterations, right? The same luxury is again coming into the fixed point iteration method. And in that sense, this inequality is very important. You should keep in mind. And not only that, we also have this result. If you recall, similar results were found in secant method as well as in the Newton-Raphson method. And from here, you can conclude that the order of convergence of the fixed point iteration method is at least 1. That is what this says, right? Because now you can take modulus on both sides, and you can see that mod R minus xn plus 1 divided by mod R minus xn to the power of 1 is equal to mod G dash of R. And as long as this is not equal to 0, you can conclude that the order of convergence of that fixed point iteration method is 1. Okay, let us prove the conclusions 2 and 3. The proof of this theorem is not so difficult once we have understood the proofs in secant method and Newton-Raphson method. Let us try to prove the second property, that is the convergence of the fixed point iteration method. You start with the error in the xn plus first iteration. You can use the mean value theorem to get g of r minus g of xn is equal to g dash of xi n into r minus xn, right? For some xi, n lies between r and xn. Now you take modulus on both sides and use the fact that G is a contraction map. It means the maximum of, it means G dash of xi n will be less than 1, right? If you recall, we have taken maximum of all the xi n's in the interval I as lambda. Therefore, I can say that this is less than or equal to lambda times mod r minus xn, right? So that is what I am writing here. And this side is just a definition. R is equal to G of R because R is the fixed point, and xn plus 1 equal to G of xn is the way we have defined the iteration, right? And that is less than or equal to lambda times mod R minus xn is coming by using the mean value theorem and our notation that lambda is maximum of G dash of xi. Now, once you have this, the same old idea of applying this inequality recursively to get mod r minus xn plus 1 is less than or equal to lambda n into mod x naught minus r, right? And we have assumed that lambda is less than 1. Therefore, this term will go to 0 as n tends to infinity. And that will immediately prove the convergence of the sequence xn. Now let us go to prove the inequality that mod xn minus r is less than or equal to lambda n divided by 1 minus lambda into mod x1 minus x naught. How will you prove that? Well, a small routine idea, mod x naught minus r can be written as mod x naught minus x1 plus x1 minus r. I'm just adding and subtracting x1, and that will be less than or equal to this, which is coming from the triangle inequality. And this can be written as less than or equal to lambda times x naught minus r, right? So this inequality I am using here. And that is what I am writing as the first term. And the second term is just retained as it is. Now you take lambda mod x naught minus r to the left hand side and then write mod x naught minus r is less than or equal to 1 by 1 minus lambda into mod x naught minus x1, right? Now you put this inequality in this inequality, we get mod r minus xn plus 1 is less than or equal to lambda n times, I'm replacing this by its upper bound, that is 1 by 1 minus lambda into mod x naught minus x1. Remember, this we have already shown while proving the convergence, and therefore that proves also the first part of the inequality. And the second part is simply a routine manipulation to get this inequality. And this proves the important inequality that is useful to obtain the number of iterations that we need in order to achieve a required tolerance. Let us finally prove this order of convergence result. Again, for that, we will use the mean value theorem, which I told in the previous slide, where xi n is some unknown between r and xn. We have already proved that the sequence xn converges to r and xi n is lying between r and xn. Therefore, in the limiting case as n tends to infinity, xi n, which is lying between these two, will also converges to r, right? Again, I'm using the sandwich theorem. Now we will use this result in this equation. Before that, we will write the equation r minus xn plus 1 divided by r minus xn is equal to g dash of xi n. Remember, when you bring r minus xn to the other side, you have to assume that xn is not equal to r for all n, sufficiently large, right? So a good argument here is to first say that for any finite n, if xn equal to r, then the iteration process terminates and we get exact result. Therefore, without loss of generality, we can assume that xn is not equal to r for all n. It's better to write that argument and then come and divide both sides by r minus xn, and then take the limit as n tends to infinity. You will have limit n tends to infinity here also. And g dash, if you recall, we have assumed g is continuously differentiable. And so it's a continuous function and xi n converges to r. Therefore, you will have this to be g dash of r. And that is what we want to also prove in order to get the rate of convergence or order of convergence of the fixed point iteration as at least 1. When I say at least 1, there is a deep meaning in that. When you have the definition of the order of convergence, that is r minus xn plus 1 is less than or equal to some constant times r minus xn, it doesn't mean that the sequence will not converge something more than 1. It can have. That is why we always say that the order of convergence, if such inequality, or in particular, if you have r minus xn plus 1 divided by r minus xn, limit n tends to infinity, because generally we impose this condition for large n of n, that should be equal to constant, right? Any of this, if you follow, it means it's only least order is 1, okay? You may have a sequence which may converge slightly or more faster than 1 also. In particular, in fixed point iteration method, such situations can occur. Say, for instance, we have taken the Newton-Raphson method formula as xn plus 1 equal to xn minus f of xn divided by f dash of xn, right? You can always write g of x as x minus f of x divided by f dash of x, and view this Newton-Raphson method as a particular case of the fixed point iteration method, right? With the iteration function as g of x given by this expression. In that case, we have already seen that Newton-Raphson method converges at least quadratically. This shows that we can also consider an iterative function such that the corresponding fixed point iteration method may lead to a quadratic convergence sequence. Newton-Raphson method is an example for that. So whenever you talk about order of convergence, whatever alpha you get, you should always say at least alpha. Order of convergence is at least alpha, you should say. Okay, this is just a remark. We have completed the proof of the convergence theorem of fixed point iteration method. Now let us go for an example. Let us take our usual example as sin x plus x square minus 1 equal to 0. And we are interested in the interval 0 to 1, in which we know that there is at least one root for this equation. There are at least 3 ways that we can consider our iterative function. Say, for instance, we can take our iterative function as minus root 1 minus sin x. Let me call it as g1. And we can also take our iterative function as sine inverse of 1 minus x square, which we will call as g2. And finally, we can also take our iterative function as root 1 minus sin x, which I will call as g3. And we will see which of these three will work well for us? Well, we know how to choose our correct iterative function. Let's go with G1 and see whether it satisfies all our hypotheses of the convergence theorem. If you recall, G1 is taken as minus root 1 minus sine x, and we are interested in the interval 0 to 1. Let us see whether it is a self map. This is the first and foremost condition that we would like to impose on our iterative function. Well, you can clearly see that it is not a self map because you have minus here. So any x naught that you choose in this interval, the next iteration will be a negative number, and in that case you will not have a value for your next iteration lying between 0 and 1, right? Therefore, G1 is not a self map. Therefore, we would not prefer to take G1 as our iteration function. Let us go to take our next proposed iteration function, G2, given by sine inverse of 1 minus x square. Let us check whether it is a contraction map. For that, we have to find the derivative of G2. Sorry, this is G2. And that is given by minus 2 by root of 2 minus x square. From this, you can show that modulus of G2 dash of x is strictly greater than 1. Well, therefore, we don't prefer G2 also as our iteration function. But let me just go ahead and compute the values of the iteration and see what is happening. And let me take my x naught equal to 0.8 and go ahead and find x1, which is equal to g of x naught given by 0.368268. And similarly, x2 is equal to g of x1. Well, it is g2 here also. Like that, you can see that the error keeps on increasing as we go on with the iteration. And in fact, you can see that this error will grow drastically. You can compute it and see on the computer, and that gives us a feeling that this sequence seems to be diverging. Let's go for our last choice, G3 of x equal to root 1 minus x square. Is it a self map as long as you restrict yourself to the interval 0 to 1? Well, you can check that. Is it continuous in this interval? That probably is easy to see. Is it a contraction map in the interval 0 to 1? Well, for that, you have to find the derivative of G3. It is given like this. Now you can see that mod G3 dash of x can be written as root 1 minus sine square x. I'm just writing cos x like this, divided by, you already have this. Well, how this 2 is coming? I think there is a 2 already here, and that 2 is carried over here, and that can be written as root 1 plus sine x by 2. And you can see that this is always less than or equal to 1 by root 2, because sine x is less than or equal to 1. You just use that fact to get this, and that is always less than 1. Therefore, G dash is always less than 1, shows that G3 is a contraction map. Let us go ahead with the fixed point iteration with G3 as the iteration function. Let us start our initial guess with x naught equal to 0.8. You can see that the error in the sequence is gradually decreasing, and that gives us a feeling that the sequence is converging. In fact, we can say that the sequence is converging because we already know from the theorem that this sequence should converge because it satisfied all the hypotheses of the theorem. And this completes our discussion on the fixed point iteration method. We have also given one more example in our notes, which gives you more deeper understanding of how the fixed point iteration method works and how to choose our right iteration function. Please go through it and make it more clear with the concepts. With this, we have finished our discussions on all the nonlinear methods that we are interested in. Let us go back and see what are all the pitfalls of these methods. Let us start with the closed domain methods. The main disadvantage of the closed domain methods is that we have to locate a root of the equation in order to start the iteration process itself. Generally, these methods converge very slowly. However, they surely converge once we obtain initial interval successfully. Coming to open domain methods, they are practically more feasible because we don't need to locate their root in order to start the iteration process. Rather, we can take the initial guesses arbitrarily and go ahead with the calculation of the iteration. On the other hand, they have restricted convergence criteria. Their iterative sequence itself may not be well defined, and even if the sequence is well defined, the sequence may not converge. Well, there are many reasons for why they may not converge. One interesting situation is that sometimes they may get into a cycle and thereby they will start oscillating. Say, for instance, let us take the Newton-Raphson method, and suppose your equation is such that the graph of the function is something like this, and you are interested in finding the root r, which is located here, and suppose you choose your x0 quite far away from r. Say you are choosing your x0 here, then you may land up in getting a iteration which oscillates between two numbers. For instance, your x1 may be here and your x2 might go like this and hit again x0, and therefore your x2 will happen to be x0, and therefore x3 will happen to be x1, and so on. If such a situation occurs, we say that the iteration is stuck in a cycle, and sometimes you want a specific root of your equation, and on the other hand, your method may go to capture an entirely different root. Say, for instance, again take Newton-Raphson method. Suppose you want to find a specific root, say this root, and assume that you have taken your x0 somewhere reasonably far from the root that you want, but not very far from it, but you land up getting a root which is much more farther than your x0. So for instance, you may be hitting your x1 here, and when you take x1, it may give you x2 here, and x2 will give x3, and thereby you are actually converging to this root, say r0, which is far away from the x0 that you have chosen. These are some of the common pitfalls that we come across in the open domain methods. This kind of pitfalls are not only for Newton-Raphson method, it can be there in secant method also, and even fixed point iteration methods can also suffer from such pitfalls.